Hi, welcome to this recording for Unit 22. This unit deals with the EM spectrum, the electromagnetic spectrum. So this emerges actually from the study of both electricity and magnetism, in which Maxwell showed that they are actually the origins of light. Basically, that's what the nature of light is. It's vibrations in the electric field and the magnetic field. And before him, actually, Mr. Young came up with measurements for the wavelength of light and also the frequency of light. But then the work of Maxwell basically generalized that into the fact that light extends on both ends. There are regions where we don't see light, so it's not really just the visible part of it that we see as and recognize as regular light, which extends all the way from red to basically blue. And that Maxwell showed that there are waves that are shorter than the wavelength of blue, and namely higher in frequency than the blue, and those are in the ultraviolet region and X-ray and gamma rays, and also showed that there are longer wavelength than the red, namely the infrared, the microwave, and also the radio waves. So that's the entire spectrum. It's relevant for us because most of the things that we study in astronomy are related to the light signature, basically the electromagnetic signature, and based on that we deduce a lot of properties of light. Okay, so of those material of those objects basically in the sky based on their spectrum. So again, what we're going to do in here, we're going to explore how wavelength and frequency are related to one another, and how we can calculate the energy. That's another work of somebody else, actually, of Planck. So we're going to use Planck's law to find the energy of the electromagnetic waves and explain what color and white light correspond to in terms of wavelength of light. And that's because of visual, because in astronomy especially we do a visual, whereas in astrophysics we use the entire spectrum. Name the different bands of light and order of wavelength. And I just mentioned them, basically the fact that there is on the longer wavelength, longer than red, and shorter wavelength, shorter than blue or violet. Okay, so as I mentioned before, they are vibrations like waves on an ocean, basically, or on a calm surface of water. Those ripples basically they represent the oscillations of the electric field and the magnetic field, okay, at the same time, hence electromagnetic waves. And those, they travel in media, and they travel also in vacuum. So in the case of light from the sun, this light emanates from the sun and travels through these ripples in space. So empty space, nothing is in there, the electric field and magnetic field by themselves, until they reach our eyes, in which case we see the sun. Okay, they are characterized by two parameters. One of them is spatial parameter. Basically, the extent between a crest and a crest is called the wavelength, or a trough and a trough is also the wavelength, or from a T0 to a T0 also it's the same length. Okay, what I mean by T0 is when the electric field is null and null the next time. I mean, you're saying in here is 0, 2, but that's 0 going in the opposite direction from high to low. We want it from the same direction. So it was going from low to high, from low to high, this distance, this distance, this distance, so they are all the same. We use the Greek letter lambda for the wavelength, okay? At the same time, we also have the frequency. The frequency is the changes in time in a given location. For example, if I pick up this point, the electric field is high right now. It's going to drop down to 0, and then it's going to change to the opposite value, and then go back to 0, and then go back to high. So this is a period, the time it takes for the changes in the electric field or the magnetic field once. The inverse of that is the frequency. So the frequency is how many oscillations are made in 1 second. Okay, so if it makes 1 oscillation per second versus if it makes 2 oscillations per second or 3 oscillations per second, or like a huge number of oscillations every second, like the case of the cell phone, for example, its frequency is 5.5 billion oscillations a second, or 5.5 gigahertz. Okay, so we use the Greek letter nu. That's basically a symbol that looks like a V for the frequency, at least in this book. Some other books they use F for frequency. Okay, so those are the two characteristics of an EM wave, an electromagnetic wave. Okay, as I said before, it ranges from deep red to violet. That's the visible light, the one that you and I see. Okay, the red is the longer of the two. It's very long wavelength, which means it's high. I mean, very long wavelength, which means it's very low frequency. Okay, compared to the violet, it's actually 700 nanometers. Nano is a billionth of a meter, or 7 times 10 to the power negative 7 meters. Again, it's an extent in space. It's a distance. Okay, that's why we use meters for it. Whereas the violet is shorter. It's almost half the red. Okay, and that's 400 nanometers, or 4 times 10 to the negative 7 meters. That's the extent of what our eyes can see. The electromagnetic waves extend far longer than 700 nanometers and extend far shorter than 400 nanometers. Those we don't see. Our eyes are not sensitive to either long wavelength or short wavelength. Your remote control, for example, is sensitive to longer than 700 nanometers, or sends signals higher than 700 nanometers in terms, longer than 700 nanometers, I should say. And your TV or your car or your door, whatever you're trying to trigger with that remote, responds to those longer wavelengths. Your cell phone, for example, is also communicates at longer, even longer wavelengths than that. Okay, your microwave in your home works with longer wavelength. Whereas, for example, the X-ray machine works with shorter wavelength. Okay, those things we don't see. Okay, ultraviolet radiation. If you go to the ocean, to the beach, for example, and you stay there exposed to the summer day, that UV radiation comes actually shorter than the 400 nanometers. So that's basically the whole point of it. Again, the colors span all the way from red all the way to violet. I mean, there are some denominations or the limits that people put in there manually, and it's probably a good idea to remember that. You have the red, the orange, the yellow, the green, the blue, the indigo, and the violet. Okay, that's actually 7 colors that Newton has basically decided to put by himself. In real life, there is no limit between. There's a continuous spectrum. Okay, it goes from 700 all the way to 400, or basically that's the extent. It starts at 700, so this one probably like 600 and something. This one is probably maybe 570 or something like that, 550 or something like that. This sits around 500. This gets around 450 or 460 or something like that. This one is around 420, and this drops to 400. Our eyes, we see colors differently. Some of us see better than others. Some of us don't even see colors. Okay, so this is basically a kind of a standard way of calling it, but that's not the unique way of dividing wavelengths. Okay. Anyway, as I said before, the frequency is the changes. So if you're sitting, for example, in a given point in the ocean, and you're staying in there, you're up and down. So you're going up and down. As the wave come in, you rise, okay, with the crest. As the wave passes you, in this case it's in here, you fall, and then the next wave will take you up and down. So you're still in the same thing. So if you're on a boat, for example, sitting in somewhere in the ocean, and no wave come by, it's going to take you up and down, up and down. That's the frequency. So how often do you go up and down? That is your period. The inverse of that, how often would you go up and down in 1 second? That's the frequency. Again, I said that we use the Greek letter nu for the frequency. We use the Greek letter lambda for the wavelength. The product of these two numbers is the speed of light, which is 300 million meters per second. Now, if lambda is long, the frequency is low. If lambda is short, the frequency is high, because their product needs to be c. As a matter of fact, if I know what the frequency is, lambda is just c over nu. So if nu is low frequency, lambda is going to be high because I'm dividing by a small number. If nu is high, then I'm dividing by a big number. That means the wavelength is short, okay? And vice versa. So that's basically the relation between the two. This relationship, this connection between the two is known as the dispersion law, okay? It really comes directly from the properties of waves in general, not just for light. Then in addition to that, we have the expression that Mr. Planck has come up with, and that is the energy of the wave is proportional to the frequency. And that's important. H is just a number. H is just a constant, 6.63 times 10 to the negative 34 joule second. It's a constant. It's a universal constant. It's one of the fundamental constants. Just like the speed of light being 300 million meters per second or 300,000 kilometers per second. H is just constant. It's called Planck's constant. But the key thing in here, so barring that constant, which is just exchange rates between how frequency is measured and how energy is measured, just basically like currency, basically between euros and dollars. Okay, in which case both of them are currency. So if you want to, the frequency is actually energy. The frequency and energy have the same nature. So the higher the frequency, the more energetic the waves are. So in the case of going back to the blue light or the violet light has more energy in it than the red light because of this connection, because the violet light has higher frequency than the red light. Therefore, violet light has more energy because more frequency, more energy. Okay. Whereas this H is just like a currency exchange. For example, how much do I need to, how much can I get for a dollar in terms of euros? Okay, so that's basically what this is. Okay. As I said before, Mr. Newton experimented with light like a lot of other people. So I really don't want you guys to get the idea that Mr. Newton invented light, or at least the study for light. This was before him and after him. So for the English-speaking people, apparently this is like a god of physics. I want to really make sure that you guys understand that other people also worked on light. Okay. His credits for breaking the light through a prism may be questionable, but there is no doubt in the fact that he basically worked a lot and mentioned it in a book about the spectrum, and he opted for the 7 lights, those Roy G. Biv. That's basically his approach to dividing light into 7 because of his religious beliefs in the 7, the value of 7, okay? Anyway, so if I run light through a prism, for example, that light breaks into different components, okay? And that is because a prism has something called an index of refraction because it breaks light. Just like, for example, water or something, it breaks light. And I mean, when light goes through it, it doesn't go straight through it. So if we send light at an angle, it refracts, okay? And that's why if you put, for example, a pencil inside a cup, you will see that the pencil appears to be broken on the edge, but it's not. I mean, where the water and the air meet, okay? And that phenomenon basically depends on the wavelength. So if you have a white color coming in, it's going to break into its components, okay? And that's why you have rainbows. Because rainbow, the light of the sun hits the droplets of water in the air. Usually rainbows happen immediately before the rain or after the rain when the air is saturated with water. So the droplet of the air, so it comes in, it breaks inside the water, and then when it emerges, the different components of light emerge, and that's where you see rainbows, okay? So this is the same phenomenon. So the index of refraction, which is how much the light slows inside the material, because it has to go and interact with the different components of it. If the material is transparent, like the case of a glass or water or prism, then it's going to emerge with different components because of the fact that each and every one of them has a different angle with which it comes out. Okay. As I said before, light is just part of the big picture, which is the electromagnetic spectrum. So this one is exaggerated. I mean, the band for visible light is very, very narrow. On one side, you have the ultraviolet, shorter wavelength. And then even shorter than that, you have X-rays. And even shorter than that is gamma rays. Those numbers that you see at the top in here are the extent of the wavelength. These lines, again, are just basically kind of, they're kind of fuzzy. So if you want to, the difference between ultraviolet and X-rays is kind of not really, it's not a fixed point, okay? It can be an ultraviolet, and all of a sudden you are actually dealing with X-rays. So it's just for our convenience, okay? We put these numbers in there for our own convenience. And that's where the CAT scan, for example, is, where you go for X-rays, for example, or something. That's where you get all of this energy. So again, look at the wavelength. It's getting shorter and shorter, which means the frequency is getting higher and higher. So if I look in here with the red line, increasing wavelengths, that means I'm shortening wavelengths on this side. But as I am shortening wavelength, I'm increasing frequency and increasing also energy, because remember, energy and frequency are the same. On the other side, the wavelength becomes longer and longer, as you can clearly see in here, and that means that the frequency is getting less and less, which means the energy is getting less and less. Sorry about that. I have my cat in here. That's very important, because that's how the sky is perceived to us, because there are different technologies, okay, that we use. So this is visible with the naked eye, how we see things. This is with the X-ray technology. We will see the X-rays. So we have, for example, pulsar that emit super energetic radiations. So they become intense in that range, less intense in the other regions. And then even gamma ray bursts that give us even super bright objects in the gamma range, but not in other frequencies. But if we are looking, for example, in the lower frequency end in here on this side, or longer wavelengths, for example, the cosmic background radiation, that is when the universe was super young and emitted light in the visible range, but because it came from very far away, and it extended, so that now it's no longer in the visible range, it's actually in the microwave. And that's where the James Webb and some of the new technologies in focus, okay? They're actually in the infrared microwave region. And there are even longer wavelength, less energetic wavelengths in terms of individual waves. But they are super intense. It means extreme high intensity in this long wavelengths or low frequency, and those are the active galaxies from the bursts in the middle, and they come as radio bursts, okay, in the radio region. That's why you see radio waves in here, microwaves, and infrared in here. And that's the opposite to the other spectrum. So the infrared will have a longer wavelengths, less energy. Microwave is even longer. Okay, we're talking in the millimeter now, up to a meter, so we're centimeters. Okay, that's the size of your the cavity inside your microwave oven at home. Okay, a few centimeters, okay? 10 centimeters, 12 centimeters. Okay, so that's 8 centimeters. So that's basically the size inside of that cavity that produces these waves. And then there is radio waves, FM, TV, and so on and so forth. The cell phone is somewhere in here. Okay, police radar used to detect people who are speeding, and so on and so forth. Okay. Again, this is continuation of the same discussion that we just did in here. Okay. The sky would look different depending on the technology that we're using to look at it. Okay. If you and I will look at, for example, at it with the this is Andromeda, the nearby galaxy, with the visible eye, basically with our eyes. Granted that we can't see it that way at all, because it's too diffuse, basically spread throughout a long time. So because our eyes have only they collect light only on a short span, so we really have to have a telescope that has a camera, for example, built on it, open for an extended period of time to collect as much light as possible. Then it's going to look like that. But if I look at the same galaxy, for example, now with the UV filter on it, okay, trying to focus on the UV emitted from that galaxy. Now I have emissions from the edges that use high energy and also from the center of the galaxy, okay? If I use X-rays, the galaxy would look basically its own center only. That's because there are far more radiation at higher frequency coming from the center than from the edges. And if I look at the infrared, where the heat is coming basically from the galaxy, it's coming from this arms basically of the galaxy in here. And even longer than that, the radio waves are coming from the edge, similar to the UV radiation, and also from the center. So this is basically how, with different technology, we say the same thing and the image changes. Now you're saying, and you are rightfully so, how in the world can we see these colors? Since you just mentioned we can see the infrared, radio waves, UV, and X-rays. We can see it with our own eyes. Yes, we have a picture right here. Yes, I agree with you. I can see this because this I can see with my own eyes. I mean, granted, the telescope is open for an extended, the aperture of the camera on the telescope is open for a long time to collect this light. But how about this two in here, or this two on the top and this two on the bottom? We can't see them. Well, let me tell you, that's actually computer rendition. If we were to see it, we don't. We can see it directly. This is how it looks like. So basically, what they do, they color code this pictures in here, with the redder being low frequency and the bluer being high frequency from that range. So if I go back to the spectrum, for example, and I'm looking into the X-rays, for example, on this side, I can't see it. You can't see it either. Okay. But on this side is going to be redder, on this side is going to be blue, and the computer basically makes that so that it gives us the impression of how it looks like if we were to see it in that range. Thank you.